Hello everyone. Declaration 1. The copyright of this article or video belongs to the original author Da Wang. 2. The content of this article shall not be reproduced without the permission of the original author. Otherwise, it will be regarded as infringement. 3. Reprint or quote the content of this article. Please indicate the source and the original author. 4. For non-compliance with this statement or other illegal use of the content of this article, I reserve the right to pursue according to law. 5. The Chinese version of this paper has been uploaded to the internet, entitled 四色猜想的证明, which can be used as a reference for this paper. Definition 21a. In sufficient graph G1, there is a subset S1 of G1 with the following conditions, called the bridge structure of G1. 1. The points in S1 are composed of the points of K1-K2 and the two bridge points bit 1 and bit 2 of K1-K2. 2. The connection relationship in S1 is composed of in G1's connection relationship between G1's component points. When K1-K2 is called the central point of G1, where K1-K2 is called the central point of G1. Definition 22. As shown in Figure 27, set S1 that means the following condition is the OD ring H1. 1. There is an origin transform structure G1 in sufficient single OD's graph G1. The front OD of G1 is K1-K2 and the rear OD of G1 is Kn-1-Kn. 2. L1, L2 is an OD ring chain pair of G1. 3. The points in S1 consist of all constituent points of L1, L2, K1-K2 and Kn-1-Kn. 4. All connection relationships in S1 consist of connection relationships between all points within the following structure in G1. A. L1 structure. B. L2 structure. C. Bridge structure with K1-K2 as the central point, G11. D. Bridge structure with Kn-1-Kn as the central point. If there is a ring LH1 set as H2 and the following conditions are met, when LH1 is the OD actionable ring and SH1 is the OD actionable region of H1 with respect to LH1. 1. The points of LH1 consist of A. All constituent points of L1, L2. B. One of the two constituent points of K1-K2. C. One of the two constituent points of Kn-1-Kn. 2. LH1's connection relationship is the connection relationships between LH1's constituent point in H1. 3. SH1 is a ring region of LH1. 4. SH1 meets the following conditions. A. SH1 contains one of the two constituent points of K1-K2. B. SH1 contains one of the two constituent points OK n minus 1 dash Kn. Theorem 10. One OD ring H1 has and only has two OD actionable rings, H11, H12, and H11 and H12 are all single rings. H1 has and only has two OD actionable regions, SH11, SH12. Proof. According to the definition of OD ring, the theorem holds. QED. Definition 23. Let the values of points in the OD ring chain pair L1, L2 of the OD ring H1 be A and B. Then C change D is applied to an OD actionable region of H1, which is called the OD ring action of H1. Figure 28 and figure 29. The latter is a graph obtained after the OD ring action of H1 to the former. We can see the H1, before the H1 change, the OD is here. And after the H1 change, the OD is here. And we can see the points, especially bit 1, bit 2, and here, all changed after the H1 action in red. One point 4. Related concepts and properties of a region-related action process. Definition 24. When the OD ring H1 acts, the two-color ring H0, where all the component points of the front OD K1-K2 and the rear OD Kn-1-Kn of H1 are located, is called the base ring of H1. Definition, the H1, we can see an H1 in figure 29 or figure 28. In 29, the base ring is this ring. Is LAD. Definition 25. In the ring action process GC1, in which the base ring and the OD ring participate, the acting base ring is called the base adjustments ring of GC1, as shown in figure 56 of Appendix 1. It is assumed that the state is obtained by the action of the OD ring of the blue base ring. The value of its contained values are A and D. If the next OD ring needs to act on the base ring composed of non-AD values, one choice is to let the blue base ring act once to obtain the red BD base ring in figure 55 in Appendix 1. Yeah, we can see figure 56. Yeah, we can see the figure 56. The base ring is here. Well, in this figure, the OD ring don't have the same the bridge with same value, so we need to make this line have a BC swap to become to make this figure become figure 55. In figure 55, the OD ring have same values bridge point of the OD. Yeah, and we can find we can decide the possible OD rings or bridge chains in the graph. You can see if there is a, because the base ring is AD and the OD ring is BC. Yeah, and we can see. Okay, now we can find a OD ring who has a chain pair with CD. You can see this CB. Okay. Yeah. So this is the OD ring responding to the base ring of this. Definition 26. GG1 is a subset of an assigned graph G0, and that GG1 has two states, ZT1, ZT2. If the value of all points in ZT1, such as K1, K2, and so on, can be changed to the value of the same point in ZT2 by finite value swap across G1, then ZT1 is called the same state of ZT2 of GD1. Figure 30 shows the state of the point inside GD1, ZT1. After AB swap and CA swap are applied to graph G0, where GD1 is located, the state of GD1 becomes figure 31, ZT2, and ZT1 and ZT2 are same states. So in the figure, we can see figure 30. It is under the operation of the following. AB swap and CA swap. We can see first apply AB swap to figure 30 is that A to B, A to B, A to B, B to A. And then C is swap. And we can see C to A to C. Yeah, we can see B, B, A, C, D, B. B, B, A, C, D, B. So figure 30 and figure 31 are the same to each other. Definition 27. There is an AB two-color ring H1 in assigned graph G1. CD swap is applied to a ring action to a ring region S1 or H1, which is called the two-color ring action or H1. OD ring action and two-color ring action have a joint name called ring action. A process of one or more continuous ring actions is called a ring action process. As shown in Appendix 1, the change process of each of the two adjacent graphs is a ring action process of one two-color ring. So we can see Appendix. So we can see Appendix 1. This is a state cycle process. And the first one is a state. And this state is changed by the CB swap of this ring. And so the BC swap, when the BC swap finished, the figure 55 changed to figure 56. Yeah, we can see CB changed to BC, and all the rest points in this ring changed. Okay, so in figure 56, there is another ring appears here, the red ring. The red ring is a BD ring, and after the AC swap, the state of figure 56 changed to figure 57. We can see CA changed to AC in this ring. So the similar operation continues. In 57, there appear a AD ring here. AD ring here. So after the BC swap of the AD ring, the state become figure 58, and so on. So the state change continues in 20 states. And finally, in figure 66, after the BC change, the BC ring changed, the BD ring, act by AC swap. The graph state, the state of the graph is changed to the initial figure 55. Definition 28. In the ring action process GC1, let its loop sequence be XL1, H1, H2, and so on Hn, headed by the H M-1 post-action state of GC1, ZTM-1. A subsequence this of XL1 is called XL2. The ring action process GC2 caused by XL1's rings from ZTM-1 is called a subprocess. Definition 29. There is a subset GG1 in the sufficient assigned graph G1, and let the subset obtained by removing the points of GG1 from G1 to be G11. The graph GG11 obtained in the following way is called the age-continuous structure of GG1 in G1. 1. Let Kj be the point in GG1 and Kg be the point of G11. 2. Kj and Kg are connected by a line LJG. 3. Randomly arrange 4 points KJD1, KJD2, KJD3, and KJD4 in G1's all the smallest region whose age LJG is on, and assign these 4 points as A, B, C, D respectively. Then an assigned graph G2 is got. 4. After removing G11 from G2, structure GG11 is obtained. We can see, maybe there's an example. Okay, we can see around the age continuous structure is here. Maybe see figure 33. We arrange the ABCD point randomly in the smallest region between the target project and the dual the target set and the dual set in the whole graph. And this, if the target structure is combined with bit 1, bit 2, K11, K12, and this structure is the continued structure of the target structure. Definition 30. In single OD sufficient graph G1, if the ring action process GC1 meets the following conditions, then GC1 is the OD-related ring action process, refers to as the origin-related process. 1. All action rings in the process pass through at least one component point of the real OD of the previous OD ring. 2. The composition values of the OD ring, chain pair, or two-color ring, or any two sequential action rings are not exactly same. So the origin-related process, we can see example here. Here. This is a diagram of origin-related process. Let's assume that we start here by acting the OD ring H01, H0-1. After the H0-1 act, the next ring is here, H1-M, maybe, no, maybe H1-1. So the real OD of H0-1 is the front OD of H1-1. Of course, there may be some ring action rings. Maybe happen here. Maybe happen here. Anyway, they all have at least one point of the composed point of the real OD of H0-1. So the process is that first H0-1, second H1-1, third H1-2, then H1-3, and so on. And this process is an origin-related process. Definition 38. The bridge structure of the point pair, such as alpha-1-alpha-2, used as OD in the origin-related process, GC1, is called the OD bridge structure. Law 1. When a single OD sufficient graph G1 is in ZT1 state, if there is an if there is no origin bridge chain, and G1 cannot obtain a state such as CT0, then origin bridge chain through an origin related process such as GC2 who does not have an OD action ring. There must be an OD related, origin related process GC1 that satisfies the following properties. 1. GC1 starts with CT1. GC1 starts with CT1. 2. GC1 contains at least one OD action ring. As shown in figure 32, when the bridge points of OD alpha 1 dash alpha 2, it is possible to assume that the component points are all A values, are assigned with C values, and L11 and L12 are AD bridge resistance, and L21 and L22 are AD bridge resistance. Although there is no actionable OD ring in this state, the L21 and L22 or L11 or L12 bridge resistance can be affected by the action of the two-color ring H1 formed by L11 and L12 or L21 and L22, and H1 passes through at least one constituent points of OD, so that the OD bridge chain or actionable OD ring will appear from the figure. In this figure 32, there's no possible OD rings because if alpha 1 dash alpha 2 is the front OD, and there's no OD rings can act in this figure. So we can see this ring combined by L11 and L12 can act to break the two red lines. Maybe L11 and L12 is maybe LAD, maybe L22 and L21 is maybe AB. Yeah. When LAD act, these two lines may become in this area, in this region. These two lines in the LAD become maybe when LAD act, the region apply BC. So B change to C. So this line become L from LAB to LAC. So here is still AB. So here is still AC. So this operation may create the new actionable OD rings or origin bridge chains. Maybe here. Definition 31. The composition values of the OD ring pairs or two color ring chains of two action rings H1, H2 are not exactly the same, which is called H1 is heterocolor to H1, H2. Law 2. In single OD sufficient graph G1, there is a region-related process GC1. If there is an OD bridge structure GG1 and the following conditions are met. 1. GC1, H1, and H2 are sequential OD action rings. 2. The rear OD of H1 and the front OD of H2 are all the central point K1-K2 of one bridge structure GG1. 3. H1 is heterocolor to H2. Define H1 and H2 satisfying the above conditions as the constituent rings of the passing OD ring pair H1, H2 of GC1 with respect to GG1. Then the following conclusions holds. 1. When the action of H1 is completed, there is K11, K12, and so on, K1m, K21, K22, and so on, K2m meets the following conditions. A. K11 to K1n exists in H1 base rings LH11, LH12, and so on, and connects to K1. B. K21 to K2m exists in H1 base ring LH11, LH12, and so on, and connect to K2. 2. When the action of H2 is completed, there is K11 apostrophe, K12 apostrophe, and so on to K1n apostrophe, K21 apostrophe, K22 apostrophe, and so on to K2m apostrophe meets the following conditions. A. K11 apostrophe to K1p apostrophe exists in H2 base rings LH21, LH22, and so on, and connect to K1. B. K21 apostrophe to K2q apostrophe exists in H2 base rings LH21, LH22, and connect to K2. 3. Define K11 to K1n as the base ring adjacent point of H1 with respect to K1, K21 to K1m. As the base ring adjacent points of H1 with respect to K2, maybe K2m. K21 to K2m as the base ring adjacent point of H1 with respect to K2. In the same way, K11 apostrophe, K12 apostrophe to K1p apostrophe are the base adjacent points of H2 with respect to K1. K21 apostrophe to K2q apostrophe are the base adjacent points of H2 with respect to K2. In the state of the action process from H1 to H2, including the state before H1 action and the state after H2 action, any K1t, K2v, and K1s apostrophe, K2w apostrophe meet the following properties. 1. K1t and K1s apostrophe are different points, and from the process, they are with different values. B. K2v and K2w apostrophe are different points, and through the process they are with different values. Theorem 10a. Any state of the origin-related process GC1, such as CT1, is a single OD sufficient graph. Proof. Suppose the state of the origin-related process GC1 is CTM before a ring action. The action ring is H, and CTM is a single OD sufficient graph GM. Let the state of GC1 after the action of H be CTM at 1, corresponding to the sufficient assigned graph GM at 1. Then there are two cases. 1. H is a two-color action ring. There are two cases. A. H consists of only one constituent point K1 of OD, and the actionable region of the H ring with another constituent point K2 of OD is S1, and the other actionable region of H is S2. Let the value of the point in H be C or D, and the value of the OD's constituent point be C. From theorem 5, there exist two color chain graphs GAB1 and GAB2, which have the following properties. 1. GAB1 is the AB chain graph composed of all points whose value are A or B in S1. 2. GAB2 is the AB chain graph composed of all points whose value are A or B in S2. 3. No point of GAB is connected to any point of GAB2. Let the CD chain graph consisting of all points of GM with values C or D be GCD. Let the action region of H be S1. That is, AB swap is applied to GAB1. Since in GAB1 there is no same value connected point pair before H action, there is no one after after the action of H. By A3, after the action of H, no point of GAB1 can form a same value connected point pair with any point of GAB2. Additionally, after action of H, no point of GAB1 can form a same value connected point pair with any point of GAB2. Additionally, as the states of GAB2 and GCD did not change before and after the action of H, there is only one same value connected point pair OD in GCD, and no point in GAB2 can form a same value connected point pair with any point in GCD. Thus, GM at 1 is still a single OD graph. B. H passes through all the constituent points K1, K2 of all OD. In this case, the proof method is same as A, which will not be described here. 2. H is the OD action ring. According to theorem 6, after the action of H, the obtained sufficient graph GM at 1 is still a single OD graph. To sum up, since the origin-related process only contains OD ring action and two-color ring action, the GM at 1 transformed by several ring actions of origin-related process GC1 from the single OD sufficient graph G1 is also a single OD sufficient graph. Theorem 10a holds QED. Theorem 11. There exists a single OD sufficient graph G1, which in state CT1 has the same state by acting once on either of the two actionable regions, S1, S2, of the same two-color ring or OD ring H1. Proof: when H1 is a two-color ring, may be said as an AB chain ring. The state of ZT1 is transformed to state of ZT2 by acting on S1 of H1, and the state of ZT1 is transformed to state of ZT2 apostrophe by acting on S2 of H1. Since the CD swap to G1 of the state of ZT2 is equivalent to acting on S1 of H1 firstly, transform ZT2 to ZT1, and then acting on S2 of H1, transform ZT1 to ZT2 apostrophe. So ZT2 apostrophe and ZT2 are same states of each other. Similarly, when H1 is OD ring, the ZT2 apostrophe and ZT2 are also same states. So the theorem holds QED. Definition 31a. In the origin-related process GC0, there are action rings H1 and H2 in the action process GC1 of the OD ring or two-color ring H1. The OD is transformed from a point pair of alpha1-alpha2 to a point pair of alpha3-alpha4. When the OD position does not change, it can be regarded that the OD is transformed from a point pair to is identical. If there is an OD ring or two-color ring H2 with the same set composition of H1, and OD is transferred from the alpha3-alpha4 point pair to alpha1-alpha2 point pair in the process GT2 of action of H2. H2 is called the same inverse action ring of H1. If GC1 is represented as H1 forward, then GC2 can be represented as H1 inverse. Remaining another conditions unchanged. If OD is transferred from the alpha1-alpha2 point pair to alpha3-alpha4 point pair in the process GC2 of action of H2. H2 is called the same co-directional action ring of H1. If GC1 is represented as H1 forward, when GC2 can be represented as H1 back, as H1 forward. So we can see this symbol as forward symbol, and this symbol as backward symbol. Definition 32. In the origin-related process GC2, if there are two sub-processes GC1 and GC2 that have no common action rings, and GC2 is the reverse arrangement of the same reverse action rings of all action rings in GC1. GC1 and GC2 are inverse processes of each other. If GC1 is defined as forward process, it is represented by GC1 forward. GC2 can be represented by GC1 backward. Remaining other conditions unchanged. If GC2 is the co-directional arrangement of the same co-directional action rings of all action rings in JC1. JC1 and JC2 are co-directional process of each other. If JC1 is defined as a forward process, it is represented by JC1 forward. JC2 can be represented by JC1 forward. Note: for the rest of this article, unless otherwise specified, all action ring process without direction identification are positive process. For example, the ring process JCX is equal to JCX forward. So the positive direction is the forward direction, and the negative direction is the backward direction. Definition 33. In a signed graph G1, there is a ring action process JC1. After each ring action of JC1, the states of G1 are ZT1, ZT2, and so on to ZTn in sequence. If the sequence ZT1, ZT2, and so on to ZTn is a loop sequence, i.e., ZTn and ZT1 are sequential adjacent, JC1 is called the state cycle process, state cycle or cycle for short, of G1, and ZT1, ZT2, and so on to ZTn is the state cycle sequence of G1. As in Appendix 1, each figure represents a state in the state cycle, and any two adjacent figures are two states before and after a ring action. After the action of the BD ring in the last figure, figure 66, the state obtained is the state of the first figure, figure 55. So I have described the Appendix 1 previously. So let's continue. Definition 34. HJ1 is a sequence combined with number of action rings, H1, H2, and so on to Hn. HJ1's rings are the action rings in JC1 action process in sufficient graph G1. The sequence of HJ1's action rings are same with their acting sequence in JC1. HJ1 is called a subprocess sum sequence of JC1. The states of a subset of G1 after the action of each action ring, e.g. H1 in HJ1, e.g. ZT1, are queued according to the sequence in which they occurred in JC1. And the resulting loop sequence, consider the first and the last state are sequential adjacent. XL11 is called the state sequence of JJ1 of HJ1. H1 is called the initiating ring of ZT1. Definition 35. In sufficient graph G1, JJ1 is a substructure of G1, and JJ11 is the edge continuous structure of JJ1. In an action process, JC1 without same state G1, JC1 has a subprocess sum sequence HJ1. If HJ1 satisfies the following conditions, then HJ1 is called the minimum loop sequence of action rings of JJ1 within JC1, refers to as the minimum loop sequence. 1. XL11, which consists of ZT1, ZT2, and so on to ZTN loop sequence, is the state sequence of JJ11 or HJ1. 2. Any two states in XL11 are different. 3. Let the initiating ring of ZTM in XL11 be HM, and at the time when HM is about to act, the state of JG11 is ZTM-1. Theorem 12. In sufficient graph G1, there is a subset of JG1 if there is a state cycle XH1 of G1 whose states do not repeat. Then there are several minimum loop sequences of JG1. Satisfy the following properties. 1. In any two minimum loop sequences, each take an element. In XH1, the action time of HM-S1 is different to the action time of HK-S2. 2. The elements in HJ1, HJ2, and so on to HJN contain all the action rings that cause the state of JJ1's H-continuous structure, JJ11 transform. Define this set is the minimum is the sequence. Define this sequence set is a minimum loop sequence distribution method set. This is the set. Distribution method set for short of JJ1. Proof. 1. Since XH1 is a state cycle process of G1, it is also a state cycle process of JJ11. Then there is a minimum loop sequence HJ1 of JJ11. 2. Let the XH1's sub-action process during two sequential acting rings H1-1, H1-2 in HJ1 be GC1. Then, according to the definition of minimum loop sequence, the state of JJ11, ZTS, ZTT is the same at the beginning and end of GC1. Then, A. If the state of JJ11 is not changed by any acting rings in GC1, do not perform any operation. B. If the state of JJ11 is changed by any action rings in GC1, set the action ring that causes the first state change of JJ11 as H1-1-1. Then there must be another minimum loop sequence, HJ2 of JJ11, and HJ2 satisfies the following conditions. 1. H1-1-1 is an action ring in HJ2. 2. All the action rings that make up HJ2, such as H1-1-2, etc., are located in JC1. Otherwise, H1-1-1's change to JJ11 can't be restored at the end of JC1, which contradicts 2. 3. Perform 1, 2, and 3 operations on all XH1 procedures separated by elements within the minimum loop sequence of known of JJ11. Since there are a limited number of action rings in XH1, all separated ring action process will be disposed to 2A states. By then, the set of all known minimum loop sequences satisfies the theorem. So the theorem holds QED. Definition 36. XH1 is an origin-related cycle process of G1. JG11 is an H-continuous structure of an OD bridge structure of G11. If the following conditions are met, JG1 is the spiral rod structure of G1 in XH1, or JG1 is the straight rod structure of G1 in XH1. That means if the following conditions are met, JG1 is the spiral rod structure of G1. If any one conditions of the following can't met, the JG1 is a straight rod structure of G1. So the conditions are: 1. In any distribution set S1 of JG11 in XH1, there exists a minimum loop sequence HG1. 2. HG2 meets one of the following two conditions. A. In HG1, there is and only is one passing OD ring pair. B. In HG1, there are 4 sequential OD rings here, which meet the following conditions. 1. In HG1, there is no OD action rings between any 2 adjacent action rings of H1, H2, H3, and H4. In H1 and H2, H1 and H2 form a passing OD ring pair of JG1, and H3 and H4 form a passing OD ring pair of JG1. Let the action process of XH1 from H1 to H4, including H1 and H4, be JC1. HD1 and HD2 meet the following conditions. A. Any base adjacent point K31S of K1 of H3 is different from any base adjacent point K21T of K1 of H2, and K31S and K21T are with different value in all states within GC1, including the first and last states of GC1. In BCD situations below, the requirement is the same. B. Any base adjacent point K32S or K2 of H3 is different from any base adjacent point K22T of K2 of H2. And K32S and K22T are with different value in all states within GC1. C. Any base adjacent point K41S of K1 of H1 is different from any base adjacent point K11T of K1 of H1, and K41S and K11T are with different value in all states within GC1. D. Any bit adjacent point K42S of K2 of H4 is different from any bit adjacent point K12T of K2 of H1, and K42S and K12T are with different value in all states within GC1. As shown in figure 33, figure 34, and figure 35, and figure 36, K11-K2 is the central point of OD branch structure, DD1. Beta 1 and beta 2 are the bridge points of K11-K12. DD1 is a spiral rod structure of X1 of G1. This set is a minimum loop sequence HD1 of the DD1's H-continuous structure, DD11. These four diagrams show the state change process of minimum loop sequence of the DD1. Figure 33 shows the state of DD11 after H apostrophe L22 action. The OD locates outside of the DD11. Figure 34 shows the state of DD11 after HL11 acting. The OD has been transformed from the outside of DD1 to K11-K22 by then. Figure 35 shows the state of the DD1 after H apostrophe L12 action. The OD has been transferred from K11-K12 to the outside of DD1 by then. Figure 36 shows the state of DD11 after H apostrophe L12 action. The OD locates outside of DD11. So, in figure 36, a OD ring is about to act, and the OD ring is HL11, and the real OD of HL11 locates here is K11-K12, and after the action of HL11, the OD is transferred from outside to K11 to K12. We can see the two component points with same value. And HL21 act in this state is about to act in figure 34. And this K11-K12 is the front OD of HL21. So after the action of HL21, the OD is transferred to outside of the DD1. DD11, okay, maybe DD1. DD11 is H continuous structure. So it becomes figure 35. And for the action rings of H apostrophe L12 or H apostrophe L22. These 2 points, maybe this connected point pair, K11-K12, is neither the friend or real OD of the 2 action rings. So after the action of H apostrophe L12, the operation after is action, the D, the K11 is transferred to A. The value is from D to A. And after the action of H apostrophe L22, the K12 is transferred to D, yeah, to become figure 66 to become figure 33. Okay. The way that the action rings this in the above 4 figures exist in JJ1 can be represented by figure 37, where L11 represents the part of HL11 in JJ1. L21 represents the part of HL21 in JJ1. L12 represents the part of H apostrophe L12 in JJ1. L22 represents the part of H apostrophe L22 in JJ1. The circle represents this. The circle. The circle represents a front or rear OD part of the action ring, and the dashed line represents the 2-color chain part of the 2-color ring or 2-color chain pair. This simplified diagram is called the visual diagram for short, of JJ1 in XH1. So this here, L11 is the solid line with the circle. And the same L21 is a solid line with circle. And L12 is a dash. It's dash line. Definition 37. In an origin-related process JC1, if 2 action rings H1 and H2 are the same co-directional action ring or same inverse action ring of each other, H1 and H2 correspond to different points or line segments at the same position of the plane. Conversely, if H1 and H2 are neither same co-directional action ring nor same inverse action ring of each other, H1 and H2 correspond to different points or line segments at different positions on the plane. At the same time, the points or line segments corresponding to the action rings with adjacent action time in JC1 are connected with lines. The diagram got by the operations above is called ring process diagram for short, of JC1. As shown in figure 38, it is diagram of the H1-1, H1-2, H1-3, and so on to H1-M minor 1 to H1-M to H0-1 and so on to H0-P to H2-1 to H2-2 to H2-3 and so on to H2-Q process in figure 38. Yeah, we can start here. H1-1. So H1-1 is the first action rings of the process, and H1-1, H1-2, H1-3 is the time adjacent or sequential adjacent action rings, and to H1-M. And to H1-M, his real OD is same with the front OD of H1-1. So the next action range is HO-1 here. Continue to HO-P and to H2-1 and finally to H1-Q. This is a diagram here from this direction.